Hello everyone, my name is Grigor Mukherjee, and today we're going to continue our discussions about the partial differential equations. And today we're going to start to learn about one of the methods of solving the differential equation. And that method is called the method of separation variable. For today's lecture, we're just going to explain what's a method of separation variable, the importance of some concepts that's really important for this method. And we're going to apply for one example, and in future videos we're going to do two or three more, I don't remember right now. And lastly, we're going to talk about the orthogonality of the functions, which is also very important while we are solving these PDEs using this method. So first, let's start to talk about the method of separation of variable. The method of separation of variables of variables, this method is used when our PDE and when the PDE with the corresponding boundary condition, the PDE and the boundary condition are linear and homogeneous. Only if both of the PDEs and the boundary conditions are both of these types, then I can apply this method to solve my PDEs. Before we start to solve it, let me talk about something that refresh your memory about the linearity and homogeneity. So let's start talk about the linearity. So a linear operator which can define, let's symbolize by letter L, is defined by the curve. If I apply the linear operator with my functions that linearly combine, then my operator will be linear if it satisfies this equation. Where my u is the unknown functions, the c's are just the constants, coefficients of constants, and the L is the operator, mathematical operator that I apply for my unknown functions. Those are, now if it follows these conditions, then it's a linear operator. And we make sure for in our PDEs, it contains this linear operation. Let me just bring an example. So the examples that we see a lot in this lecture. For example, if I do partial derivative with respect to time, and I take, let's say, C1 U1 plus C2 U2. In this case, my L is my partial derivative with respect to time. Therefore, if I expand this using the knowledge about the derivatives, I get partial t C1 U1 plus partial derivative C2 U2. And since it's a constant, like they become as a coefficient, and I can take it out in front of partial U1. So it's a partial U1 over partial t plus C2 times partial U2 partial t. Now, here you can see it's just L of U1, and this is L of U2. So this is my partial derivative partial t is a linear operator. Similarly, the second order partial derivative with respect to x, that's also linear operator. Now, any linear combination of linear operators is also a linear operator. Linear operator. Now, suppose let's consider recall our heat equation, where my partial u partial t is equal to k times second order derivative u with respect to x. Okay, now let me just rewrite this expression slightly different. So take everything in one side. That's equal to 0. This also I can rewrite this as partial t minus k u is equal to 0. As you can see, this is my linear operator L that I apply corresponding u. In this case, this operator is known as a heat operator. It's called a heat operator. When you take the quantum mechanics class, you learn like a momentum operator, kinetic energy operator, position operator, and etc. They have their own equation, and they're Hamiltonian, etc. So they have their own equation, and it's pretty similar what we're doing. We're just only discussing the linear operator. Any linear equation, the linear equation for a non-function u is in the form of the linear operator applied to my unknown function is equal to a certain source of function. And my certain source of function must be linear too in order to be a linear equation. Now, let me do example. So the example can be like, again, not going far away, our heat equation plus f of x of t, because this I can rewrite as partial t minus apply to u is equal to my f of x t, which is pretty similar to the form that we have. Additionally, any linear operator, for example, if my heat equation is something like this, let me just write the heat equation really quick. Now let's say plus another arbitrary function in the position time, and I have a u plus t. This is also linear. I just multiply one additional function too. That's still a linear. However, for the example for nonlinear, it contains nonlinear operators. For example, if my heat equation is something like partial t, that's equal to plus alpha xt. Now I apply the u to the power 4. The main reason this is nonlinear because the power 4 is my operator that applied to my function u, and that u to the power 4 is not a linear either, because I will just be quick, because a plus b to the 4 does not equal to a to the 4 plus b to the 4. Similarly, the square root a plus b is not equal to square root a or square root b, or ln of a plus b, because that doesn't equal to ln of a plus ln of b, because these are not a linear operator. It doesn't satisfy the condition that required. So as long as you you understand the main idea, the definition, you will be fine. This is a simple basic concept. Now let's move on. If my f is external, there's no sources at all for my linear equation, therefore the linear equation is become equal to 0. Specifically, if there's no outside source of the function, nothing besides all my unknown function one side, and there's no other besides the unknown, it's called a linear homogeneous equation. This is called as linear homogeneous equation. Yes. So the otherwise, like for example, this one right here, this is a non-homogeneous. Homogeneous. Okay. Also, for our method of separation variable, we also again, it's applicable to use the principle of superposition. The principle of superposition. I'll write in red for the definition, which states that if u1 and u2 satisfy linear homogeneous equation, then the arbitrary linear combination of them, then the arbitrary linear combination of them, in this case, like most common way is c1u1 plus c2u2, also satisfy same linear homogeneous equation. Homogeneous equation. We can do a simple proof for this. So let me write the proof. So we apply the u1 and u2 are my solutions. So the linear operator applied to u1 is equal to 0, and the linear operator that's applied by u2 is also equal to 0. Then I use if I use the general definition of my linearity, so to check, constant times u1 plus arbitrary constant u2. Now I applied my linearity, CL of u1 plus c2, the linear operator apply u2. Now since L of u1, L of u2 is equal to 0, 0 plus 0, that's also equal to 0. So this is the simple proof. Okay. One more thing, science, we talk about the linearity and homogeneity just applied to our PDEs. Also, we have to consider that the linearity and the homogeneity also applies to the boundary conditions, to the boundary conditions. It's also applicable to my boundary conditions. Okay, and similarly, same examples for the boundary conditions. You just, instead of x, you just write either x equal to 0 or x equal to L and have the same format. As long as it's the same format, you are fine. Okay, now based on our understanding what is required, let's start to solve the example of PDEs using this method and considering both linearity and homogeneity. So our example for solving it is called the heat equation with zero temperatures at finite segments. Okay, so this is our example. So the corresponding PDEs, so my PDE is just my heat equation, and assuming there's no sources right here. Okay, and this is valid. So we are talking about the finite ends. So my x is between 0 and L, and my time is expected to be positive. Okay, nothing new. Now let's talk about my boundary condition. So my boundary condition is zero temperature at the finite segments. So what I expect is u at x equal to 0 at the given time, it should be equal to 0, and then u at x equal to L time is also equal to 0. And to avoid the uniqueness, like non-uniqueness, we're gonna consider an initial condition by saying that my u of x comma 0 is defined as f of x. Okay, so this is my PD with the corresponding boundary condition and initial condition. So as you can see, we have a linear operator, which is stated here, right? And we have a linear operator. There's no outside sources, so it's a homogeneous. And we have a linear and homogeneous boundary conditions. We don't care about the initial condition. So all these things satisfies, right? Because of the definitions of separation must be linear and homogeneous. We have those. So we can use this method to solve our PDEs. Now let's write. So the method. In the method, our educated guess is that our unknown function u of x of t is just the product of the function of x and the product and the function of t. Okay, this function that consists of only x, and this function that consists of only time. Now we use this. This is called a product solution. This is called a product solution. Now, the one thing you have to understand that our initial condition doesn't matter here. We only care about to find a corresponding solution that's applicable both my boundary conditions and the PDEs. The initial condition is just the last thing you have to worry about. As long as your boundary condition satisfies your initial condition, it's easy to figure out. Now, let's solve this. Let's substitute our guess solution into PDEs. Now my partial u, partial t, which is equal to partial t of phi of x g of t. Now I'm taking the partial derivative with respect to time, therefore all my x components will act as a constant and I can bring it in front. So therefore on the left side I have a phi of partial g partial t. Now let's do on the right side. So my u of second order with respect to x, again I apply to my solution. Now similar reason as did before, since I'm taking with respect to x, all my time component become a constant and I can take it as a coefficient. So it's become a g of partial phi partial x squared. Now I have this PDEs. Now I can rewrite my PDEs this way. So phi of partial g partial t is equal to k times g partial phi partial second order with respect to x squared. Now if I do the next step that I'm going to do, this is where names come from, separation of variable. So I'm separating all the time components on one side and all the x components on the other side. So therefore my corresponding PDEs is become 1 over kg partial g partial t, that's equal to 1 over phi second order phi squared. You don't have to take the k on the other side. At the end you're going to end up the same solution. I just did this because it's easier to multiply on both sides, so I prefer to do this way. Now let's think about this. On the left side, I only have the t, no x components, only t. While on my right side, I only have the x component, only x. So two independent variables that are independent from each other, they are equal to each other. That only can happen if and only if they both are equal to a constant. So my constant is going to symbolize as a negative lambda, and that negative lambda, and that constant is known as a separation constant. Separation constant. It's just an arbitrary constant. While solving our PDEs, you will find which values of lambda that is required that will help us that satisfies these corresponding boundary conditions. Now, having all of these, therefore I can separate my PDEs into this format. Now, since on this left side, wanting to consider my partial derivative with respect to time, the g is only composed of time, no other variable. So I can write ordinary derivative instead of partial, because in this case, the both will be the same thing, since my g is only considered time. Similarly here, since my phi is only a function of x, and I'm taking the derivatives with respect to x, so it's going to be ordinary derivative. So I can rewrite the same differential equations instead of partial, I can write it ordinary. So partial x squared, and I multiply all the coefficients on the other side, and I got is equal to negative lambda phi and lambda phi, and my partial t partial g, so my ordinary derivative of g with respect to time is equal to negative lambda jk. Okay, now let me take this to this side. Okay, so now the product size, my product solution must satisfy to my boundary conditions. So I have to see how does my boundary conditions will satisfy. Now, if you notice, my boundary conditions vary. That doesn't depend on time. It depends on x. Varies at x. So therefore, my boundary conditions here is going to be even only for x. So I can rewrite. So my boundary conditions this way. Now, for my u of 0 t is going to be equal to phi of 0 g of t. Now, here, this is only, so now since my phi of 0 is equal to the g of t, if I use the zero product property, I'll get that either phi of 0 is equal to 0 or the g of t is equal to 0. Now, if my g of t, now why is acceptable this but not this? Since when we're solving the differential equations, we are trying to avoid the trivial solutions. Now, if my g of t is equal to 0, therefore my u will always become a 0. So therefore, for non-trivial solution, this is only can happen if my phi of 0 is equal to 0. And similarly, for phi of L, that's equal to 0. Because again, u of L of t is equal to phi of L times g of t, that's equal to 0. Now g of t cannot be equal to 0. Now I can just write here as a wrong, different color. Because of trivial solution. Okay. Well, if you notice, my g of kt doesn't have a boundary condition because my boundary conditions only depends for x. So here I'll say no boundary condition applied. Okay, now let's start with the time dependent of equation. Okay, you will see why I'm starting from here. Time dependent equation. in my corresponding PDEs, my time-dependent equation has this form. The ordinary derivative t that's equal to negative lambda jk. And I can solve this PDE, this ordinary differential equation, using the separable variable. So now I can have dg over g that's equal to negative lambda k dt, and I can integrate both sides, and I'm left with natural log of absolute value of g that's equal to negative lambda kt plus arbitrary constant d. Therefore, to get rid of the natural log, I'm taking the exponential both sides. Absolute value of g is equal to e of negative lambda kt plus d. Now I can, and then therefore my g is equal to plus minus another constant like e of d times e of negative lambda kt. And this can be simplified, therefore my g is equal to a big constant c times e of negative k lambda t. Now, my time-dependent equation also contains my lambda here. Now, as I mentioned again, the lambda is arbitrary constant, and only certain values of lambda can be acceptable. Let's look this time-dependent case to see which lambda has been allowed in my PDEs. And then I will use the x-dependent part, and then you will see like they kind of matches together, and you will see which one more accurately required for my corresponding PDEs. So let me start from here. So the my lambda can be three values. Lambda can be positive, lambda can be negative, or the lambda can be equal to 0. Okay, this is the only three cases that can be valid for my lambda. Now, let's look for lambda that is positive. If I substitute my positive lambda into my equation, I could see that this exponent is going to be negative. The negative exponent, and I take the power of e, that's going to be decay. So therefore, for positive lambda, I have an exponential decay. Exponential decay. Now, for lambda that is negative, this will make my exponent positive, so I will get an exponential growth. So my lambda that is negative is called exponential growth. Exponential growth. And lastly, for lambda is equal to 0, I will just get the constant. So it's just going to be constant, and it doesn't change in time. So I can say it's a constant in time. Okay? Now let's analyze this to see which one required. If you remember our heat conductions, as it approaches, time goes on and on and on, our temperature becomes a positive. So that's the heat is flowing the outside, and heat is conduct. So therefore, I expect only it decays or it just remains a constant. Because only in those cases, my temperature can be decay into 0, or it can become constant. And that's because from my product solution, my u of xt is just proportional to the g of t, right? And so we do not expect any growth in exponential. Do not expect exponential growth. Therefore, allowable lambda are greater than or equal to 0. Now, why we cannot use this time-dependent equation to more accurately determine what is our lambda? The main reason is because we don't have the boundary conditions, because our PDS must satisfy the boundary condition. Every boundary condition has its corresponding function, 5x, which is considered our eigenfunction. And for each eigenfunction, we have our eigenvalues. And this lambda represents the eigenvalues. So let me introduce called the boundary volume problem. Boundary value problem. Now, in this case, my second order differential equation is equal to negative lambda of phi. Okay? And I have these two conditions. Why this doesn't call the initial value, not the initial value problem, instead of boundary, because why it's not called the initial, instead it's called a boundary. The reason is because we have a conditions at two different places, not at the exact same place. We have two exact different places. So that's why different locations. So that's why this is our boundary condition. This is called a boundary volume problem. Now, if I solve my ODE, from ODE, I will see that I also still have 3 cases for the lambda, which will yield a different solution. So, let's recall your memory again, solving the second order differential equations, taking everything to the one side. Now, applying our ansatz, where my phi is equal to just the exponential of r of x. Now, substitute that, I will get the r squared e of r of x plus lambda e of r of x. That's equal to 0. Therefore, my r squared plus lambda is equal to 0. Therefore, my r squared is equal to negative lambda. Now, again, as I mentioned, the lambda can be 3 different values. Therefore, now, if my lambda is a positive value, now, if it's a positive value, therefore, I get the r squared is equal to negative lambda. Therefore, my r is become plus minus I times square root negative lambda. So I get 2 imaginary roots. 2 imaginary roots. Imaginary roots. Now, for a lambda equal to 0, I get r squared that's equal to 0. Therefore, my r is just equal to 0. And I only get, again, one solution with multiplicity of 2. City of 2. So you have to have 2 roots. One is 0, the other one is 0 as well. And then lastly, for a lambda that is negative, now my r squared is equal to negative lambda. Therefore, this thing is going to be positive. Therefore, my r is equal to plus minus square root negative lambda. And I get 2 real roots. 2 real roots. Now, let's study each case separately and you will see that which one is acceptable. So far, using the time dependence, we only see that only lobel is greater than or equal to 0. But here, when we go this using the boundary value problem, we're going to get one of these. Either lambda is greater than 0 or lambda equal to 0. Since both must be agreed, so we know that this is not going to be acceptable. So let's study the case where lambda is greater than 0. Now, I have my ODE. Therefore, my phi and my r is just equal to plus minus I times square root negative lambda. Now I can, therefore my solution is going to be a constant 1 times e of positive I negative lambda x plus arbitrary constant e of the conjugate of it, x. And I will apply the Euler's formula. Applying the Euler's formula, so I get C1 times the cosine of square root negative lambda x plus sine I times sine square root negative lambda x plus C2 times cosine of square root negative lambda x minus I times sine square root negative lambda x. Okay, now I hate when this is happening. Now I can apply, since it's gonna be C1 and C2, I can just write constant d times the cosine d1 cosine of negative lambda x plus the constant d2 sine negative lambda x, and where my d1 constant is just defined as c1 plus c2, while my d2 constant is defined as c1i minus c2i. Okay, so this is my solution. Now let's apply the boundary conditions. Let's apply the boundary conditions. Now, I have phi of 0 is equal to, now if I substitute 0, it's going to be d1 because cosine of 0 is 1 plus d2 times the sine of 0 is 0, it's become d2 times 0, that's going to be equal to 0. Therefore, simplifying it, it gives me that my d1 is equal to 0. Okay, no other chance. Now, if I apply for phi equal to L, So my D1 is equal to 0. I can ignore this part. So I got D2 sine square root negative lambda L. Now, if my D, and that's equal to 0. Now, if my D2 is equal to 0, I will get a trivial solution. So for non-trivial solution, for my non-trivial solution, my sine of negative lambda L is equal to 0. The one thing I noticed I did a mistake is this. Huge mistake. This should not happen, I apologize. I just realized it. It's embarrassing, I apologize again. Okay. I noticed something is going wrong, but could not find where was that going wrong here. Now, this is equal to 0 if and only if my square root lambda L is equal to integer multiple of pi, and therefore my lambda is equal to n pi over L squared. And you have to also indicate that n is positive integer. Now in the future you don't have to consider, because in the final result you will see why I have to accept positive integer. You will see why. Now, so this is my lambda is my eigenvalue for my eigenfunction of x. Eigenfunction of x. But this is only case when my lambda is positive. Now, let's look when my lambda is equal to 0. Okay, so let's look at this case 2. So the case when my lambda is equal to 0. Okay, in this case, I will get that my second order differential equation is going to be equal to 0. Right? And this is true if and only if. Now, I can do two ways to do it, but we know that this is true. The solution is going to be the equation of the line. C1 plus C2x. Or the way you can do it, it's the equation of the line. But if you want to explicitly show that it's the equation of the line, now I know my r is going to be equal to 0 with the multiplicity of 2. Multiplicity of 2. Therefore, my phi is equal to C1 e of 0x plus C2x times e of 0 times x, that which is equal to C1 plus C2x. Okay, now I apply the boundary condition. Apply the boundary condition. I got, so for phi of 0 is equal to C1 plus C2 times 0, which is equal to 0. Therefore, my C1 is equal to 0. Now for phi of L, that's equal to C2L, that's equal to 0. Therefore, my C2 is also equal to 0. So therefore, lambda equal to 0 is not an eigenvalue. Okay, and the last case, case 3, when my lambda is negative. Now, in this case, my ODE become negative lambda phi, so it's become a positive thing. Therefore, my R squared is gonna be equal to negative lambda, and therefore my R is equal to plus minus square root negative lambda. Therefore, my eigenfunction, or my phi, the solution of this ODE, is going to be equal to C1e positive this x plus C2e negative x. Well, this is the combination of the exponential functions. So I can rewrite this in terms of the hyperbolic functions. So I can rewrite this as a C1 cos of square root negative lambda x plus C2 sinh square root negative lambda x. Okay. Now, let's apply our boundary condition. So apply our boundary condition. So I will apply using this part. That's much easier than doing hyperbolic functions for me. So phi of 0 is equal to, so I got C1 plus C2, that's equal to 0. Now let's look at the second one. Phi of L is equal to C1 times E of square root negative lambda L plus C2 E of negative square root negative lambda L. Now, I can simplify this since I have two unknowns, two equations with the two unknowns. This must be equal to 0. Now, I can solve that my C2 is my equal to negative C1. Substituting there, I get C1 E of square root negative lambda L minus C1 E of negative square root negative lambda L. Okay. Now if I simplify even more, I get the factor of C1 E of square root negative lambda L minus E of L. This thing will be equal to 0 if my L is equal to 0. This thing will equal to 0 if my L is equal to 0. Because in both cases it's equal to 1. So 1 minus 1. But here they are different, and L is not 0 because we are looking in a finite segment from 0 to L. So L cannot be equal to 0. So this is equal to 0 if and only if my C1 is equal to 0. And if my C1 is equal to 0, therefore my C2 is also equal to 0. And I get a trivial solution. So therefore, lambda, in this case was negative, is not the eigenvalue. Is not eigenvalue. Now, let's summarize. If we summarize, our eigenfunction for this corresponding is just 5x that's equal to a constant times sin lambda of L. So it's equal to my 5x is equal to a constant d2 times the sine n pi x over L, where my lambda is equal to n pi over L squared. This is my eigenfunction, and this is my eigenvalue, corresponding eigenvalue. Okay, so we solved our x component. Now let's go apply, now we all have our product solution. Now we're going to apply our superposition principle. So recall the superposition principle. The superposition principle states that if we have multiple solutions, u2 till u some certain u sub m, which are our solutions of linear homogeneous problem, then any linear combination of this is also solution. So here I'll write this. So this is going to be my solution. One, C of n, U of n. Now if my series, I write this in this term, already showing it that my n is a positive integer because it's starting to 1 and it goes to the m, something that's greater than 1. So therefore, this I expect, like, this shows that my n is a positive integer, so you don't have to separately specify. If you do, that's good for you. Now, applying this superposition principle, therefore, applying the superposition principle, my u of xt is just equal to the real assume starting n equal to 1 and goes to m. Now since I have a constant d2 here and another constant for my time dependent part c, if I multiply them together, they're still going to be a constant. So that constant is, I will call it bn, because each for n value of n, they have different constant, and that's equal to sine n pi x over L. That's my x dependent, and my time dependent. Now my time dependent also contains the lambda, so I'm going to substitute the lambda, which is going to be n pi over L squared times k times t. Okay, this is my solution. This is the solution of linear homogeneous heat equation. Okay, now we have to apply the, since this b of n is not unique, we do not have a unique condition because they can be any arbitrary constant, so it must satisfy to our initial condition. So therefore, applying the initial condition, initially our u of x0 at t equal to 0, my time dependent is moving away because e of 0 is 1. So I have is equal to, we can assume m, n starts 1, pn sine n pi x over L. And since my initial condition at beginning was given a certain function of f, so therefore my initial condition must be equal to f of x. Now we're going to use this to solve my b of n using something called the Fourier trick. It's called the Fourier trick. Now, in the future, in the next, after this solving separation variable method and Laplace equation, we're going to talk about the Fourier series. But right now, I will recall the theory. The claim theory of Fourier series states that number one, any function f of x, it can be represented as a finite linear combination of, in this case it's a sine n pi x over L. So far this is what we have here. The second part is for small m, for small m, it's not the approximation may not be good or very good. So therefore, to get more accurate, increase the value of m, which is m goes to infinity. As it goes infinity, the better the sum gets. And lastly, consider m approaches to infinity, not only it's the best approximation, but also the resulting infinite series will converge to f of x. Okay, now let's do the Fourier's trick. So to solve this Now using the Fourier trick, which will help us to solve our PDEs to get the unique solution. By first considering the orthogonality of the sign. Orthogonality of in this case, our function is sine. Now since our Fourier series function is just the infinite one of sine n pi x over L, which hold over region of 1D of the one-dimensional rod. And if you remember, our x is just between 0 and L. Now, in the Fourier trick for this orthogonality, Fourier's trick, using the orthogonality of the sign. So before introduce, the orthogonality of the sign is that going over the entire region, multiplying two the sign functions that has a different values of n and m that are orthogonal to each other, now these things can be equal to two values. Now this can be equal to two values. Now let's see, if our n is equal to our m, therefore our integral is become just the sine squared of whatever n pi x over L dx. Then I can integrate this, that will give me 2L over 2, right? So the one solution is that I will get L over 2 for n equal to m. The second part of the solution, if they are different values, if my n is not equal to m, then now my integral will be the 0. This is for n that's not equal to m. Now I can rewrite my solution as L over 2, 1, 0 for n is equal to m. If you don't know, this is called the Kronecker delta. Did I spell it correctly? Let's just make sure. Kronecker delta, which can be simplified as L over 2 delta of n m. So it's either equal to L over 2 or it's equal to 0. Now, what's the Fourier trick? The Fourier trick now if you notice, just I have sine n pi x in one side, so I can just multiply the another eigenfunction that is orthogonal to my sine. I will just multiply this in both sides and integrate over the entire region. So what I say is I integrate, so integral 0 to L f of x times sine of mix over L dx. That's equal to, now I'm multiplying same on the right side. So 0 to L infinity n equal to 1 p of n sine n pi x over L times sine n pi x over L dx. Now my Riemann sum and B of n are independent of x, so I can write outside of the integral. So get 1 b of n, the integral of 0 to L sine n pi x over L sine n pi x over L dx. From above, this is equal to L over 2 delta n m. So this equal to n equal to 1 b of n times L over 2 delta n m. So I will sum over my n. So I will get, so now my n is equal to every value. So my n is equal to 1 while it has different value of m. So I will get 0. If I get the n equal to 2, I'll get 0. I will get 0. My sum will be 0 as long as my n is not equal to 1. The only time L is not equal to 0, the only time my delta n is not 0, if my n and m are equal to each other. So when my n is equal to m, I can just multiply L over 2. Okay. Now if I try to solve my B of m, therefore my B of m is going to be 2 over L integral 0 to L f of x sine n pi x over L dx. Now I can change m to n because they are dummy indices. What the heck means dummy indices? The meaning, if I change the letter n to m, it won't change the meaning of my equation. Therefore my B of n is equal to 2 over L 0 to L f of x sine n pi x over L dx. Therefore my solution of the heat equation with 0 temperatures at finite segments is, so my u of xt is equal to the Riemann sum. I can just substitute B of, I will just write the B of n here of sine n pi x over L times E of negative n pi over L squared kt, where my b of n is equal to 2 over L integral from 0 to L f of x times sine n pi x over L dx. So this is my solution for that PDE. And let's finish this about what the heck I mean orthogonality, which is going to be very short. The orthogonality. Let's recall the dot product. Recall the dot product. The dot product of any two vectors is equal to the scalar product of their magnitudes and times the cosine of the angle between them. The dot product is equal to 0 if and only if my theta is equal to pi over 2, meaning u vector and v vector are orthogonal. Now the analogous here, instead of the dot product, is just the integral. If from 0 to L, any two eigenfunctions with their corresponding eigenvalues over the region 0 to L, their product is equal to 0. Therefore, my a of x and the b of x are orthogonal. Over the region 0 from 0 to L. So in our case, the our eigenfunction is just the sine, and the corresponding eigenvalue is the lambda. And then lastly, a set of functions, that each member of which is orthogonal to every other member is called orthogonal set of functions. This orthogonality will be really useful because the farther we go to solve the PDEs with the different boundary conditions, we still have to consider the type of eigenfunctions and eigenvalues, and when we apply the initial conditions, we have to use this Fourier trick, which is based derived from this orthogonality, that will help us to find our unique solutions that we are looking for. This is all we have today for you. For the next lecture, as I can repeat it, we're going to solve another PDE using this same method, but with different boundary conditions. The notes will be uploaded on my Instagram account. Thank you so much.